Good afternoon. Can everybody hear me and see the PowerPoint slide?
Yes.
Okay. Are there any questions?
Will you put the halting problem on the final exam?
There will be some question related to that, yes. I'm not going to spend an entire week talking about it and not putting it on the exam.
Gotcha.
When is the final? Whenever the official schedule says. Find out. Last I know is on the 2 to 5 p.m.
Yeah, it's May 10th.
Any other questions? So we're getting pretty close to the end of this course. I don't think I have an entire hour and a half for today, but it can surprise me. And on Monday, I will only answer questions, so I hope you have some questions. Just not planning to cover anything new. The grades for the exam 3, I have asked the TA to have them posted by Monday. So that's where we're operating. That's how we're operating. Any other questions? So the task that we have to complete, which we started but never proved it, is to answer the question, is there a language that is RE but not recursive? We have made some arguments about such a language, but we have never really shown that it exists. And you can make all kinds of arguments about things that don't exist, and you can derive all kinds of interesting things about things that don't exist. So it is absolutely crucial that we actually establish that this isn't just some chimera, that there are in fact languages that are recursively enumerable but not recursive. Now, I've hinted at a language that would be satisfying it, but I haven't proven it, and it is fairly complicated. You'd actually have to first show that the post-correspondence problem is undecidable, and then you use the post-correspondence problem to show that there are two grammars, context-free grammars, for which it is undecidable whether they are generate the same language or not. So there is a candidate, but we haven't proven it, and actually the proof that we're going to use is somewhat simpler. But it starts with an issue that is perhaps intellectual, also somewhat intriguing, and that is a universal Turing machine. universal Turing machine U, which basically does what the name suggests. Given an encoding of a Turing machine, M, and an input string X, U, that universal Turing machine, accepts the pair consisting of that encoding M and X, if and only if M accepts X. So basically, you have here your universal Turing machine, and you have essentially two inputs, an encoding of a Turing machine, M, and a string X, and it will, well, what can we expect that Turing machine U to say? Can it give us yay or nay?
Yeah, it would either accept or deny the word. Right?
That's not true. Remember, this is an arbitrary, M is an arbitrary Turing machine. In particular, we do not know whether it will halt on input X. So the universal Turing machine will say yes if M accepts X. But it does not necessarily do anything. In fact, it may just continue spinning its wheels if M does not accept X. So this is a little tricky. So what we have then is the language LU, which is the set of all pairs M and X, such that X is an L of M. Keep in mind that this in no way makes any statement about what happens if the X is not in L of M. That is precisely the issue that we're concerned with. So this is a language L sub U that basically takes M and X. So in other words, this L of U is effectively what the universal Turing machine U does, and it will take M and some X. There, of course, presumably, if L of M is infinite, there are infinitely many X's that are in L of M. And so there are obviously infinitely many Turing machines. So this is a fairly complex issue, L of U. But basically, for any Turing machine M and any input X, if X is in L of M, then it will accept that pair M and X. And now the claim is LU is recursively enumerable, but not recursive. So this is then the answer to that question that I posed here. So that means that all we have to show now is that LU is in fact recursively enumerable but not recursive. That's two parts. Is LU recursively enumerable? Well, that's obvious. Yes, by construction. There is our Turing machine, this universal Turing machine. How does it work? Basically, it takes that description, the encoding of M, and then very laboriously jumps back and forth and simulates M on input X. You can imagine there is quite a bit of technical detail which I'm going to spare you. Basically, the easiest way is probably to assume that the universal Turing machine has more than one tape. You can easily see that a Turing machine with two tapes can be simulated by a Turing machine with one tape. It takes a lot longer, but you can certainly pretend that it is only one tape, and you then use that one tape to simulate two tapes. So that is probably the easiest way to see that on one tape you have the encoding of M, and on the other tape you have the actual tape where the X is sitting, and so then you work with that, and M basically allows you to simulate the Turing machine, the encoding, so that you can go back and forth and look up the a particular move, which of course you can obviously compare, and so you can find out what it is. This is certainly not the kind of thing that you actually want to do in real life because it is slow as hell, but it certainly can be done. So whatever that Turing machine M that is given by its encoding does on that input X can be simulated by that Turing machine U, universal Turing machine U. So what that means then is that what we have here is a Turing machine, and that of course is ultimately all that needs to be demonstrated in order to show that that language LU is recursively enumerable. Here is the Turing machine, and because there is a Turing machine that defines L sub U, it follows that L sub U is recursively enumerable. And now we have to see whether LU is not recursive. So how do we show that? Well, if indirectly, say LU is recursive. Well, then that means, of course, that LU complement is recursive. Okay. That means that there exists a Turing machine for LU complement that halts on any input. And now, let's go back to that language that we defined last time. The set of all Wi such that Wi is not in L of Mi. So the Wi WIs are an enumeration of all words of the alphabet of input symbols, and the MIs are an enumeration of all the Turing machines. Now, we've already shown that this is not RE. That was something we did last time. So this is not RE, and if you now look at what is LU complement, well, that is basically the negation of that. So it would be X not in L of M, which, if you ignore the M, which is just syntactic, if you have that image of a two-tape Turing machine, then it becomes very clear that the M is not really that relevant for that purpose. It's just M to capture the enumeration. So you have LD is essentially the complement of LU. And since LD is not recursively enumerable, which we shown last time, it follows that LU complement can't possibly be recursive. And so if LU complement is not recursive, then we clearly have the situation that LU complement, which is essentially LD, which is not RE, it follows that LU is RE, which we've shown already, but not recursive. So we've now seen an example. It is not the most intuitive example, I grant you that, but it is certainly the easiest way to prove it. As I said, if one were to show something more intuitive, that would be significantly longer, and it still would ultimately involve reducing the post-correspondence problem to the halting problem of Turing machines, which of course is that dichotomy between LU and LD. So LU and LD essentially are complements of each other, and if you recall, if you take an arbitrary language and its complement, then they can either both be recursive or both could be non-RE, or one of the two is RE but not recursive, and the other one is not RE. And this is precisely the situation that we're encountering here. LU is essentially the complement of LD. LD is not recursively enumerable. LU is recursively enumerable, and therefore it cannot be recursive, because if it were recursive, then it would create a contradiction to the three cases, L and L complement both recursive, L and L complement both not RE, or one of the two RE but not recursive, and the other one not RE. These are the only two possibilities. So in this case, LU being RE, the complement then is necessarily not RE, and that then implies immediately that LU, which is RE, cannot be recursive. So we have now shown that LU is recursively enumerable, but not recursive. So let's look at a few examples that will probably allow you to slide. Okay. All right. I forgot to do that earlier. Usually I do that before, so now let's do a few of these. Okay, here is an empty slide. And so let's look at the following question. Is L empty? And let's say L, well, I will look at 4 cases, okay? Is L empty? I'm sorry, empty, not empty, everything, not everything. So these are basically 4 different questions. And now let's assume that L is recursive or L is RE but not recursive. Now, this is a little tricky, and let's start with the second question. Is L not empty? Now, perhaps we should start with a simpler question. Is W in L? Now, W in L, that's of course the fundamental question that defines recursive versus RE, but not recursive. Okay, if you think about it, well, this is of course recursive, meaning that you will be able to say yes or no if L is recursive. So you have a Turing machine for L which halts on any input, and so if I give you the question W in L for some W, then obviously this is a recursive problem, because all I have to do is run the Turing machine for L on W, and because by assumption L is recursive, that Turing machine is guaranteed to halt on every input, in particular that input W that we're providing and asking about. And so is W in L is a question that has an answer yes or no. And that makes that problem recursive, because we will always have an answer yes or no. Because clearly, if the language is recursive, there's a Turing machine that will halt on every input. So in particular, it will halt on input W, and it will tell us, yes, it is in the language, or no, it is not in the language. So this, by definition, then makes that a recursive problem. Everybody clear about that? Now, what if L is recursively numerable but not recursive? Well, again, this is fairly straightforward. If W is in L, then that Turing machine for L, in this particular case, RE but not recursive, is going to halt and say, yes, W is in L. But if W is not in L, then that Turing machine may not halt. And so in that particular case, the answer again is fairly straightforward. This is RE but not recursive. So that means that we can get the answer, yes, W is in L, because the Turing machine is guaranteed to halt eventually. We don't know how long it'll take, but we know if the word is in the language, then it will be accepted and the Turing machine will halt. Conversely, if the word is not in L, then the Turing machine is not guaranteed to halt, and therefore we may not ever get an answer no. So we get yes, which is, of course, this example that I illustrated here. There is yes, but I certainly didn't write no, because that would mean recursive. Okay, so this is essentially a restatement of recursive versus recursively enumerable but not recursive. And now let's look at the second question of those four. We want to know whether L is not empty. Now, if L is recursive, then this is fairly simple. We can basically enumerate, so let's call this 1, enumerate all words and test for each word whether it is in L. Now, this, of course, is always going to be yes or no, whether that word is in L. There will always be a yes and no. It will always halt, and so I can take the first word and test it, and it will halt with telling me yes or no. And if it says no, then I just go on to the next word, W2, and I do the same thing. And if it still says no, it's not in the language, I go to the third word, and so on and so forth, until I find a word WI in the language, at which point I will say it is not empty. Now, what if I don't find a WI in L? Well, in that case, that process will not terminate. So that means that this case is RE, but not recursive. Because you cannot arrive at the answer, this is not true. So it is recursively enumerable because I just gave you a Turing machine, essentially, that will give you the answer, yes, it is not empty. There is a word. But at the same time, if it is not true that this is not empty, empty, if it is in fact empty, that process will continue indefinitely. So it is recursively enumerable but not recursive, which of course then immediately implies, if this is number 2, this immediately implies that 2 is not RE. Because it would have to say, yes, it is empty, but in order to do that, that doesn't work. So this is obviously the complement of that. Since this is RE, but obviously not recursive, this must therefore be not RE. And if you now play the same game with the other 2 questions, well, here you want to find, so if this is number 3 is very similar to number 1. In this case, of course, we're interested in a word that is not in L rather than a word that is in L. So we continue testing, and as long as we have a word that is in L, then we go on to the next one until we find a word that is not in L, in which case we can immediately say this is RE but not recursive. Come on. And the same thing then goes for number 4, which of course is exactly the same as 2. And so this is not RE. Okay, so that was what if L is recursive. Now, what if L is RE but not recursive? Now things are a little bit trickier. We still have the same 4 questions, but there will be some differences. Let's again start with number 1. When we assumed that L was recursive, we could simply take a word and test it, and the answer was going to be yes or no, and then once we had that answer, we could go on to the next one. Now, if L is RE but not recursive, we can't really do that. Because if the first word is not in the language, then that first word may never terminate. So what we have to do then is come up with a somewhat trickier idea. So here's our enumeration of the words W1, W2, W3, W4, W5, and so on. Obviously, this is not going to terminate. And now I'm going to do the following. I have here 1, 2, 3, 4, 5, and so on. And this number, 1, 2, 3, 4, 5, obviously it's not going to terminate either, will do the following. It will be the number of steps that I am doing on processing a word. So initially, I take the first step for processing W1. And then I go to the first step of W2. And then I do the second step of W1. And then I do the third step, so this is 1, 2, 3. Then I do the first step of W3, which is 4. The second step of W2, which is number 5. And the third step of W1, which is 6. And then I go first step of W4, second step of W3, third step of W2, and fourth step of W1. And so on and so forth. So what you can see in this is that you are going to look at every possible step. Now, obviously, it is conceivable that some W terminates, and so you can just ignore that, and that's not really a problem. So in some sense, what I'm writing down here is maximal. If some of those steps are not necessary, then you can just ignore them and skip them. But what you can see here is that if you want to get step I of word WJ, you will get to it. Don't ask me how efficient it is. It's, as I said, inefficient as hell. But it will work. You will, whatever step I is, 10, a million, 10 trillion, you will get to that step on whatever word you're interested in, which means every word is eventually going to be dealt with. And so in that way, you will actually determine whether there is a word that is in the language. Okay, in that way, you're going these diagonals, and so the next one would be step 1 for 5, step 2 for 4, step 3 for 3, step 4 for 2, and step 5 for W1. So obviously for every word, eventually, you're going to have as many steps for a particular word as you need in order to be able to determine that the word is in the language. Now, it will not terminate if the word, it may not terminate if the word is not in the language, okay? But if there is a word, W5, that is in the language, then you will get as many steps as are necessary. This is, of course, unlimited. And eventually, if, say, W5 is in the language, then the Turing machine will halt on W5 and will say W5 is in that language, and therefore you will be able to answer this question. Is L not empty? And so what that means is this is still recursively enumerable, but obviously not recursive. Okay, And so by the same token, of course, this is not RE. Same argument as before. This one is recursively enumerable, but not recursive. Therefore, the complement, which this is of that, is obviously not RE. Now, let's see what happens with the third question, this question, which I denoted by 3, which is, of course, the last of the 4. What will happen here? Okay. We can, of course, try to do the same thing as we did here for words, and that will find a word that is in the language. The problem with that is that if L is RE but not recursive, if there is a word that is not in the language, which would then show that L is not equal to A star being everything. So if there is a word that is not in L, that word doesn't necessarily hold for L. So we can obviously do the same trick as we did here, but the problem is it will only tell us for a recursively enumerable but not recursive language that the word is in the language. But that's not the question we're interested in. We're interested in whether a word is not in the language. Is there a word that is not in L? And so that means we can't really answer that question. So this is not RE. And obviously the complement of that is also not RE. Because in this case, we want to find that all the words are in L. And that means we would have to be able to show for every word that it is in L. There are infinitely many, so the answer to say yes to this question is obviously not something that can be done in a finite amount of time, and therefore that means it's not RE. So that gives you a little bit of an idea how these things work. So perhaps let's look at one more example. And before we just looked at a single language, now let's look at two languages. The union of L1 and L2. And so the question is it empty? Well, let's start with not empty. Is it empty? Is it not equal to A star? Or is it equal to A star? And so what if L1 and L2 are recursive? And what if L1 and L2 are RE, but not recursive? So if L1 and L2 are recursive, then basically the first question, is there a word that is in the union? If both are recursive, then of course we're back to this question. The first question, is L not empty, which for the language L recursive we said is recursively numerable but not recursive. Well, for the union, we can obviously run two Turing machines in parallel. We do the first step for the first Turing machine, the first step for the second Turing machine, second step of the first Turing machine, second step of the second Turing machine, third step of the first Turing machine, third step of the second Turing machine, and so on and so forth. So in that way, we are guaranteed to do whatever we have to do. And what we do with each of those Turing machines is, of course, testing for each word whether it is in the language or not. And of course, if one of those two Turing machines, the one for L1 or the one for L2, says yes, a particular word is in that particular Turing machine, then of course we can immediately say this is not empty, and so this is RE, but obviously not recursive. By the same token, of course, we immediately then can see that the corresponding complement is not RE. That, of course, makes this question a special case by simply saying L1 and L2 are exactly the same language. So in that way, this question reduces to this question. And if this is not RE, then obviously this one is not RE either. The third question that I have here, again, we can now look at the complement, because both L1 and L2 are recursive. We can then test whether there is a word that is not in the union. Again, you run the Turing machine for L1 and the Turing machine for L2 in parallel, the way I've described it. Step 1 of M1, step 1 of M2, step 2 of M1, step 2 of M2, and so on and so forth. That obviously effectively is equivalent to running them in parallel. And because they're both recursive, if at some point both of them do not contain a particular word, then we can immediately conclude that this is not everything. So L1 union L2 is not A star, and so that makes it RE, but not recursive. And testing whether they contain everything is obviously then, again, not RE. So what you can see in this case is that in addition to this processing of all words, W1, W2, W3, and so on and so forth, you then can do the parallel processing of Turing machine for L1 and the Turing machine for L2. Now, when we go to both being RE but not recursive, we then have to go back to this trick, where we essentially ensure that if there is a word that is accepted by a Turing machine, then we will find that out. So if we find a word that is either accepted by the Turing machine for L1 or by the Turing machine for L2, then obviously we will get to that using this trick. Remember, we had to do that trick because if we start with a word, that word may not be in the language, and therefore the calculation would never terminate. But because we make sure that every word is going to be gotten to, we get to every step I of every word WJ, no matter what I and J are. In that fashion, we then know that this is again RE, but obviously not recursive. So in this case, we do that trick, which in a way is sort of parallel processing of all words, except, of course, in a somewhat haphazard fashion. And then we superimpose the parallel processing of two Turing machines. That's, of course, much easier because we're looking only at a finite, at two Turing machines that we do in parallel. So we do, as I said, this is something for Turing machine 1, and then we have something like that identical for Turing machine 2, and so we do one step for Turing machine 1 and one step for Turing machine 2, and so on and so forth, alternating. So in that way, it follows that okay, this is not RE, that follows. And so we can test for that. I'm sorry, I'm getting ahead of myself. So I'm still justifying that this is RE but not recursive because I'm doing this for both M1 and M2, and I can do that in parallel, and that gives me RE but not recursive. And now if I take the complement of that, then this is obviously not RE. And now, if I want the union of L1 and L2 not being equal to A star, I basically would have to find a word that is not in that union. And that is not possible because L1 and L2 are RE but not recursive. So that word that is not in L1 union L2, it can very well be a word where they will not terminate, and so this will make them not RE. And obviously equal to A star is also not RE. So that means we now have effectively the same conclusion if you compare those conclusions with the conclusion for that single language. Well, they happen to be exactly the same because it really isn't much more difficult to do two things in parallel than to do one thing in parallel. One thing. You don't need parallelism. Okay. So that gives you a bit of an idea how these kinds of decision problems are evolving. If you took the intersection, the answer would be exactly the same, and so on and so forth. So you can see how these results are arrived at. The primary trick is, well, there are two tricks. You can run two Turing machines in parallel. That's sort of a fairly simple trick. Step 1, Turing machine 1, step 1, Turing machine 2, then 1 for M1, 2 for M1, 2 for M2, 3 for M1, 3 for M2, 4 for M1, 4 for M2. So that is fairly trivial. Much more interesting is this idea of doing essentially an infinite number of words, because obviously that enumeration is infinite, there are infinitely many words, and if one of those words is such that a Turing machine would not halt, then obviously that would give rise to an infinite number of steps for that word, and obviously that will not terminate. But if you have a word that is accepted, then it will terminate within a finite number of steps. I don't know how many, and I can't give you even an estimate, but I know there is a finite number of steps within which that word will be accepted, and then it will halt and will say that word is accepted. So for some word you will be able to say that, and so that is of course the reason why we can decide that this is not empty. This is RE but not recursive, and obviously if we want to know whether this is empty, then that's not going to be doable. So that basically is all I wanted to say about decision problems, undecidability, and the kinds of problems that you can derive answers to. How is that problem solvable? Say, is it empty? Is it not empty? Is it everything? Is it not everything? And depending on what kind of properties you have for the languages, in this case, if both of them are recursive, then you get those answers. Not empty is RE, but not recursive. Empty is not RE. Not everything is RE, but not recursive. Everything is not RE. And if then both of them are RE, but not recursive, well, you can find a word that is in one of those two languages. This is union, so if you have a word that is in one of those two, then obviously the union is not empty, and if such a word exists in either L1 or L2, you will find it in a finite number of steps, and you will be able to answer, yes, this is not empty, so this is recursively enumerable. But obviously, if there is no such word, then you will never terminate, so this is not recursive. So that then is the situation depending on whether you have recursive or recursively enumerable but not recursive for your languages L1 and L2. Any questions? That's basically all I wanted to say.
Professor, I have a question.
Yes?
All right, so this is more so that we can actually try to implement this. So in what you did right now, you actually did is it recursive, is it not recursive? The aspect of this would, in a question that we would have to answer in the test, would it be enough for us to do a picture of like how like the picture like in slide number 3, and then just say that it
Yep,
is
that
okay.
would be sufficient.
Okay, so then my other question would be like how to postulate this type of questions. It seems like there's 4 different events that you mentioned, whether it is there, whether it isn't there, whether all of it is there, whether there's none of it there, right? Um, is
Yeah,
that
that's for that. These are examples. Obviously, one can do all kinds of more complicated things. But yeah, these are the 4 cases that I think are useful to just go through and illustrate 2 aspects basically. The fact that you can parallel process 2 Turing machines. So whatever each of those Turing machines can do, you can do one after the other, interlaced. You see, the point is, of course, the interlacing is important because if you say I'm going to do word 1 on Turing machine 1, well, word 1 may not terminate on Turing machine 1. So you have to interlace things. You can't just say I'm going to do first word 1 on Turing machine 1 and then word 1 on Turing machine 2, because word 1 may not ever terminate on Turing machine 1, therefore you would never get to Turing machine 2. So you have to do that interlacing business. And the same thing then at a slightly more complicated level, because now you're looking at an unlimited number of words, again being interlaced. Word 1, step 1, word 2, step 1, word 1, step 2, and then word 3, step 1, word 2, step 2, word 1, step 3, and so on and so forth. You can go down these diagonals, and in that way you're guaranteed, no matter what I and J are, you are guaranteed to get to step I of word J. Okay?
what do we do to stop it? And like let's just say that word 1 does not end. Do we have anything right
No,
now?
it will not. Well, I mean, when you say what do we mean, when does it stop? Well, if we find a word that is in either accepted by Turing machine 1 or Turing machine 2, then we can say, yes, this is not empty, and therefore we can terminate.
Okay, so in this regard, the Turing machines are not actually computers, but they're hypothetical machines that are working
Yeah,
with.
you don't really want to build a Turing machine.
Okay.
You can do these things more efficiently in other ways. But as I said when I introduced them first, Turing machines are the most powerful system that you can imagine. There is nothing that anybody has ever come up with that is more powerful than a Turing machine. Now, this is the church Turing thesis, because obviously nobody can prove it. You can't prove that something can't be more powerful, but everybody is convinced that whatever you can do with a Turing machine. Not very efficiently. That's a separate issue, but that's not really what this is all about. This is not about efficiency. This is just about, can I do something or can I not do something? And not being able to do something, well, that is the equivalent of something not being RE. And being able to do something in a limited way is RE but not recursive. Of course, if you are interested in W in L for some W, well, that is recursive. That will answer yay or nay one way or another if the language is recursive. If it's not, if it's RE but not recursive, then that question is RE but not recursive. That's fairly obvious. Any other questions?
When is the last lecture?
This was it.
Okay, so this is the time.
Monday I am simply reserving for questions. Well, your questions and my answers. So in contrast to the usual lecture where I ask questions and I hope answered them, Monday I'm not going to ask any questions. Maybe leading questions, but by and large, I'm not going to cover anything new on Monday.
Is there anything that has, like, I know that we're talking about quantum computing now. Does that have anything to do with a Turing machine or how the Turing machine is used?
No.
Okay, so that's completely different in terms of what's
Totally different. Whatever you can do with quantum computing is still subject to the same kinds of requirements about decidability. If there is an undecidable problem, a Turing machine is not going to do a damn bit for you. Or, a quantum computer is not going to do a damn bit for you. I mean, if it can't be done, it can't be done by a von Neumann machine or by a quantum machine. Quantum computing is primarily about efficiency, if you believe in quantum computing. And I think I've already told you that I am not a believer. And that really has more to do with physical properties. I mean, if you have a quantum computer, then yes, there are certain things we can do much more efficiently. The problem is that I do not believe we will ever have large-scale quantum computers, physical quantum computers. Theoretically, yes. I mean, if you give me a quantum computer with 500 qubits, then the current secure public key infrastructure is dead. You can forget about buying anything securely on the internet if you give me a quantum computer with 500 qubits. But I don't believe there ever will be one such beast. Now, of course, if you are a conspiracy devotee, then you probably believe that the KGB or the NSA has already one of those things and listens to everything that you say and write. I'm not quite that paranoid. Any other questions? You want me to go through the slides so you can take pictures? Slide 1. Slide 2. Slide 3. And slide 4. We only got to 4 slides today. That is it. So on Monday, come up with questions, ask questions, and I will give you answers. If there are answers, I mean, if you ask questions that have very little to do with the content of the course, I may not have an answer, but if it's related to the course, I will be able to answer it.
I have a general question.
Yes.
What would you, how would you describe something that, because the Turing machine is a theoretical model. How would you describe something that is, let's say, for example, a compiler that is uh, that has Turing machine capabilities?
Well, a compiler doesn't have Turing machine capabilities. It's a different type of animal. A compiler basically is a single purpose kind of thing. It will process a program, determine whether it's a valid program, and then execute it. So yes, you could say in some sense it might be considered a universal Turing machine, because obviously you can write a universal Turing machine in some programming language and the compiler will compile it and execute it. But it is a much more limited, at some level it's a much more limited kind of thing. A Turing machine basically can do everything that you can imagine. Compiler, probably not. But these are very different concepts. The Turing machine basically probes the outer limit of what is doable. I mean, effectively, if you write a program, you are implicitly assuming that that problem that you wrote the program for can be solved. That's not really necessarily the question that is posed when you look at Turing machines. Turing machines really have to do with things that are more complicated. I mean, if you remember, we said context-free languages. Well, with some exceptions, most programming languages are sort of context-free. There are additional requirements that come, but most of the syntactic properties of a programming language can be described using a context-free grammar, where it goes a little bit beyond the requirement, what you can describe in with a context-free grammar is when you get into issues that variables have to be declared before you can use them. So at that point, that would not be, can't be modeled using a context-free grammar. But if you factor that type of, if you will, semantic requirement out, then virtually all programming languages are specified using context-free grammars. And all the parsing that is going on is essentially done using context-free grammars and parsers based on context-free grammars. And so from that point of view, Turing machines go well beyond that. And while you can obviously write, and probably many of you have, an infinite loop, which would be the equivalent of a Turing machine not halting, you probably will not argue, you will not want to argue that you did that deliberately, you screwed up. Whereas in Turing machines, if you have a language that is recursively enumerable but not recursive, then every Turing machine for that language will have the defect, if you will, that it won't halt on input that isn't in the language.
Okay, thank you.
You're welcome. Any other questions? Well, in that case, come up with questions for Monday so I can provide you with answers. Have a good evening.
Thank you, Professor. Bye.
Bye-bye.